Hello, today I'm going to talk about valves, the type of valves used in PCP air rifles. PCP being pre-charged pneumatic. Now these valves, usually you've got two valves per rifle. There's the firing valve that controls the speed the pellet is launched down the barrel, and then there's the non-return valve or refilling valve that holds the air in. So the air is trapped between the front valve, the refilling valve, and the firing valve, and that's where your air, that's the pre-charged air that we're talking about. In this instance, you've got a refilling valve that, in our case, looks like this. You've got on the inside, you've actually got a filter to make sure that no dirt comes in. You've got the attachment here for attaching the charging device. This is actually a cover that goes on and covers it while you're using the rifle. When you actually want to recharge it, what you actually do is you take the recharging adapter, put it on, it goes onto two O-rings, put this one on back to front, and then you can charge the rifle from anywhere that way around. Now then, I will describe the valve in a lot more detail when I go onto the computer and show you exactly how it works. The other valve is the firing valve, and this is the valve for the other end. In fact, in this particular rifle case, it's this valve. You can use either or. This is one firing valve, and that's another one. They're two completely different designs. And this is the hammer hits this, pushes it open, and that allows the air to come up through here and down the barrel. But I'll show you that in more detail when I switch to the computer, which I'm now going to do. So here we are. This is the non-return valve. This is a non-return valve, and this is a fairly early CAD system we're seeing this one on. So that's the thread that we saw in the other video. That's the front thread there that this screws onto, and this is the filter that screws in at the back of it. Now then, I will now show you the inside of this valve. So remove this first of all, so you can see inside of it. Here you see you've got the inlet here, and the valve is in the closed position at the moment, so no air can come back out. And when we actually pressurize this area, this valve opens. I'll move this just to make it a little bit clearer. And then if I open the valve, open that valve there, now then, the air can now flow in through here, up through there, and you'll see that there is a slot there to enable it to go through the slot and out through here. So in this condition, air is flowing from here through and in and charging the rifle. Then when you disconnect the pressure, the valve closes and it is then completely shut and no air can come out. The cover cap is this one, and that just sits on there, and those two diameters there locate across here in this case, and actually make sure that it cannot leak even if the valve leaked. It's just a second, it stops the dust going in and any air that may have been in there coming out. However, the secret with this valve is that material and the shape of this seat. That's what makes this valve work, and work for many years without failure. Whereas a lot of valves today, they'll work initially, but they don't last very long. This valve, in my experience, we've had these running 25 years and they've not leaked. Not always going to be the case, but more often than not, yes it is. So there we have the refilling valve. This is a typical arrangement of a firing valve. Before I explain how our firing valves work, which are very much more controlled than the average valve, I need to show you how a basic firing valve works. Here we have what would be the high pressure area. You'd have the non-return valve there with a tube of air, and the air is trapped here by this valve being shut. When we want to fire that pellet, this hammer strikes this valve stem, moves the valve open, the air flows through here, up through there, and pushes the pellet out. Let me show you that a little more clearly. So the hammer comes down, strikes the valve stem, pushes the valve stem open. The air now is flowing from here, up behind here, and in behind the pellet, and that's pushing that pellet out through there. The problem we have is that this air is such a high pressure, we were talking sort of 200 bar in many cases, that is flowing through there, and that is keeping this valve open because the valve can't shut because the pressure build up behind there is preventing it from closing. That valve can't really close until that pellet exits the barrel, lets the air out behind it, which then enables that valve to shut, and then the hammer stays in the rest position. Now this is fine, but in actual fact you've got a high pressure blast of air going all the way down to the barrel until it exits this end, which is why a lot of rifles are very noisy, because they've got a lot of air in this area. But in reality you don't need the air flowing there. You need the air to flow, accelerate the pellet, and then for this valve to close, and that's a different sort of valve altogether. And that's what I'm going to show you next. Before we leave this simple valve system completely, perhaps I should explain what is required to change the power levels of this type of rifle in this situation with this type of valve. Basically, this is acting as a non-return valve at the moment. High pressure air is in here trying to get out, can't because it's been held shut by this valve. The pressure on here is relatively high, and the only way you can knock it open is the kinetic energy of this hammer. This hammer has a spring behind it, so the heavier the spring, or the heavier the hammer, the harder it will hit and the further it will open. And the further that it opens, the more air that flows through. Now, this is fine, but you don't have a great deal of control over that, because this pressure is going down with every shot. And this is fairly constant because in fact you've got the same spring, the same weight, and it's hitting this valve stem. So what tends to happen is that as this pressure drops, this valve opens further, which in fact it needs to do, because as that pressure drops you need more of the low pressure air to get the same performance from the pellet. So it's working partially in your favour, but it is quite important to understand, and in fact the way that the adjustment actually happens at this stage is the more energy you put in here, the more energy you'll get out of there because you hit the valve open slightly further. It's just as simple as that. It's just a case of the wider that valve is open, the more air that will flow. The other fact worth mentioning is, in actual fact, putting more pressure in here does not make the rifle any more powerful. In fact, it works the opposite way. If you were to push that to say 230 bar, that would be being held shut much more rigidly, and this would be unable to open it properly. In fact, you could get to the stage where it couldn't open it at all, and you probably wouldn't fire any of the air. So what tends to happen is that there is a happy medium whereby this pressure here is about right, that matches the energy that's been put in there, which gives you the best sweep performance of the rifle. Very often that's somewhere between about 150 bar, probably down to something like 90 bar. Below that you won't have enough power, and above that you will have less power again. So these are just points that I would like to mention, because I think there's a misconception that the more pressure you put in here, the more powerful your rifle will be, and that isn't the case. Okay, here we have the body of a black fox valve that I designed back in 1994. And what I'm about to show you may make you wonder why 23 years later other manufacturers have not caught up, with the possible exception of Daystate and their electronic system, which has probably gone way beyond. Here we go. This is a section through that valve. This particular rifle actually used two tubes. The power tube at the front, and you had the tube at the rear end, which housed all the firing mechanism. It was just the way that the Black Fox rifle worked. You had the rotary breech was around here, so the air would come out of there and go down the barrel via the rotary breech. This is a volumetric valve. You have a volume in here, and this is the volume of air that is used to fire the pellet. This is filled from the high pressure area here, which is you pump up to 180 bar, and the air feeds through there into this chamber all the way around here, which in fact is the air used to fire the pellet. When the rifle is fired, like so, the valve stem is opened, but the hammer hits the end of the valve stem. The valve stem opens. This opens the valve. Air from here flows through there, up and down the barrel. Now, the air coming out of here causes that pressure in there to drop, but this O-ring here on the valve head seal is actually seeing pressure from there. It's coming through a metered orifice here. So consequently, that pressure's dropped, this pressure is high, so that closes that very quickly. So the amount of time that valve is open for is very short, and consequently it uses much less air. It's much better controlled as well, because in fact, as the pressure in here drops, the pressure in here drops as well, but in fact that means this is held shut with less force, so when that hammer hits it, it opens a little bit further. But that brings in not only just inlet port number 1, but in fact, if you look at the body, you'll see that in fact there are 4 ports around the outside of the body, and they are stepped. They come further away. So in fact, basically, as the valve opens further, it actually brings more ports into bear, and consequently increases the flow rate through here. But it is controlled nonetheless. The size of the ports, the size of all the valving is carefully calculated to make sure that everything runs as it should. Now then, this is a very much more controlled valve than anything you've probably seen before. It's simple, it's not difficult. It looks more difficult than it is because of the extra tubes here, but the valve itself is very, very simple. And this particular rifle, some of our test rifles, when we were testing them, they were putting every shot through a half-inch long by 5.5mm wide slot, which was 0.22. Up and down the target in the very centre. All the shots were going through that from the very first to the very last. That's how controlled this valve was. Here we have the body of the Nimrod valve. This is a valve designed in 2003 for use in the Nimrod rifle. This one is again a volumetric valve where you've got an accurate controlled volume of air in here, so that when the valve opens, the air flows from there to there, and it's recharged from the high pressure side here through there and out through there. Now then, so that when this valve is fired, that pressure drops, allowing this valve to be closed by the weight of this spring, which is controlled here. In its fired position, the valve stem has been knocked open, the O-ring there to prevent any leakages. This is opened, air is flowing from here through the notches in the centering ring. This is a flat valve seat. We find this to be more efficient and less likely to get debris than the tapered ones. And it's also got a stop on the end here to stop overheating, so in fact the furthest that can open it is to that point. We don't want it to go any further than that. So basically this valve is reasonably well controlled. I wouldn't say it's got the same degree of control as the Black Fox, but in fact it turned out to be a very efficient valve and extremely accurate. In connection with the Nimrod valve, we used this hammer system. This hammer was sliding on a fixed shaft. This was the little carrier. When that hammer was actually fired, it hit the carrier and then continued it forward and pushed the valve open. But this carrier was made of acetal, and there was this acetal buffer which you saw previously on there as well. So there's no metallic content here at all. So this valve was very silent in terms of metallic noise when it was fired. Then when this valve is pushed shut, it comes back and it pushes this carrier back against that stop. So consequently there was no rebound and therefore no hammer bounce, which tended to mean that in fact the valve shut and stayed shut. So consequently it just made it that much more efficient and kept everything very quiet. The combination of these two together worked really well.